So let me quickly show you what we did last time, then I'll go from there. So we're talking about the moment of inertia matrix. Okay, so this was what we were talking about. So moment of inertia matrix has 9 components, and we can use the formula to find the find each component. So the formula is here. So this is the formula we are going to use to find the 9 components. Okay, so how can I do that? How can we do that? So let's do one problem. Hopefully that will clarify the concept. Okay, let's do one problem here. So what is I? Let me begin with IXX. Okay, so what is IXX? IXX is let me write this down here. IXX is triple integral, volume integral, y square plus z square, rho dx dy dg. Okay. So let me start with that. Then, okay, that's my IXX, right? So in this case, what is my? So can you give me the in this picture, right? What is the limit? Because my this is the solid. Okay, let me explain about this picture here. So this picture is uniform and solid block, not cube, but it's not cube, but it's rectangular, not the cubical. So meaning ABC not equal, not necessarily equal. So in this case, I have you are given that the coordinate system is right in the center, geometrical center of this body. So this is given. Okay, so put the system put the frame right at the center of the object, geometrical center. So then what is the limit of integration here? Can you help me here? What is the limit of integration? So let me begin with G component. So this is Z. So Z is so my system is right in the middle, right? So G should go from negative C/2 to positive C/2 because the total is C. Does it make sense? That's for the Z. Z is done. Now how about the Y now? What is the limit for the Y? So this Y, this is right in the center, meaning so negative B/2 to B/2. Then similarly for the X, you have similarly my negative A/2 to A/2. That's my limit. Okay, so far so good.
Is oh, okay, my bad. I think I see. So dy and dz are crossed out at the very end of our
no, this is the product of dx, dy, and dz. This is what I.
Oh, you're just underlining them. I apologize.
Yeah, okay,
okay.
yeah. So dx, dy, dg.
Okay.
Okay. So how do you integrate this guy? So let's do one by one. So which one you want to do first? You want to do x first, then we'll do y, then g, right? So we have y and g here. So I can write negative C/2, C/2. Okay. Similarly, I can write negative B/2 to B/2. Then let's do the integration with respect to x here for this one. Let's do this integration here. So with respect to x, right? So that's why y and z constant for x. Okay, so y square plus z square is constant for x. Okay, then what is yeah, rho is also constant, obviously, right? Rho is also constant density. Then what is the integration of dx? Simply x, then integration limit from negative a over 2 to a over 2, right? Then x is done. Now you have dy dz. Now I have 2 more to go. So then plug in the value of it is simply like this. So x negative a over 2 to a over 2. What is the if you plug in the value, what do you get? A over 2 minus a over 2, which is simply a, right? So this guy simply gives me a. Okay, so negative c over 2 negative c over 2 negative b over 2 to b over 2. Okay, so so rho y square plus z square. And this,
Pardon me, Professor. Could you move the page down just a moment?
oh,
Equals A. Okay, thank you.
yeah. So then this is simply a. Then dy dz. Okay. Now you have to do the integration of this guy now. This guy here. What is the integration of this guy? So a and rho, they are constant, right?
Oh, my bad.
Yeah.
Would it wind up basically be the same thing, just x with the line and then b over 2, negative b over 2, winding up equaling to b? Or we're integrating with respect to y right now, right?
Yes.
Okay. So I'll just watch. I'm sorry. I'll see if I'm correct.
So this rho and a, they are constant, right? So we don't have to worry about that. Rho and a are constant. Then what is the integration of the y square dy? Y cube over 3. That's the y square integration. Then z square is constant for y. That's why you simply have z square there. Z square is constant for y. Then so g squared dy. So g squared dy integration is y there. So then the limit is negative b over 2 to b over 2. Now you have dz again. This dz, right?
Oh wait, I apologize. So now our y is y cubed over 3, and then is that z squared times y?
Yeah, so because we are doing the integration with respect to y, right?
Right.
So that's why we have 2 terms here, y square dy and z square dy. Okay.
Oh, so that's just the integration process.
Yeah, y square
Okay.
dy plus g square dy.
Okay. It's been such a long time
No,
since
that's
I've
fine.
done integration.
That's fine. So then if you integrate the y square dy, then you get y cube over 3. So
Okay.
if you integrate z square dy, then you get z square y, because z square is constant with respect to y.
And we didn't do anything with x because x wasn't in there to begin with.
Yeah, so x is already done.
X is already done. Okay.
So yeah, here x is already done. This is the x, this is the y, then we have to do the z.
Okay.
Okay. So, and then how do you simplify this one now? Let me do the next page. So what do you do here? Put this little bit up here. Can you see this guy here? Okay. You can see it here, right? Okay. Now how do you do the integration of this guy? So you have y cube over 3g square y. So what is the integration of, so this is what I meant. What is the integration of y cube over 3 plus g square y negative b over 2 to b over 2? What is the integration of this guy? So here 1 over 3 b over 2 cubed minus b over 2 cubed. That's for the first term. Then plus z squared, okay, b over 2 minus b over 2. Does it make sense so far?
There's no difference between the parentheses and the brackets, right?
No.
Okay.
I randomly chose.
Just making sure.
Yeah, I know. That's fine. So then what is this guy here? So this is 1 over 3. So b, this is b cubed over 8 minus, this is minus here, right? So you get minus minus plus here. So b cubed over 8 also. Plus z squared. You have simply b here, right? So if we do that, 1 over 3, this is 2b cubed over 8 plus z squared b over b. Yeah, z squared b. Okay. So here 2 times 4. So b cubed over 12 plus g squared over b. So what does this give you? It gives you b, you can take b outside, right? So factor it out. So b squared over 12 plus z squared. So far so good?
I think so.
Okay, now this guy is done. This guy is done. This part is this guy. This part is this guy. Okay.
Oh, could you go back to that sheet just a second? Oh no, the other one where we were figuring out the b. Thank you very much.
Okay. So then this guy, as you know, this guy is this guy here. So you have to just plug this in there. So what do you get? You have to, if you plug this in, then you have to have row A. So let me do it here. Row AB, then this guy is this, then DG. Then the integration, right? Negative C over 2 to C over 2. So we have to integrate this final integration now. We have to do the final integration. So far so good. Remember, what is the value of this guy? This guy is this guy here, right? This is this guy here, right? So what I did is b square over 12 plus z square. I plug this here. So when I plug that in, then you have row A, B, right? This is, you have row A and this is B. Row A, B, that's what I have here.
Mhm.
Then this whole thing, this is a circle thing, is this guy. So B is already there. So B square over 12 Z square. B square over 12 Z square. Then dz.
Okay.
So now finally we have to do the integration of this guy here. So obviously this row A is constant, right? Row A, B is constant. So how do you do the integration of this guy here again? Row A, B is constant. The integration of, so you have two terms there. What is the integration of B square over 12 dz? Integration of B square over 12 dz. B square over 12 z simply, right? Then what is the integration of z squared? Z cubed
Z
over
cubed over 3.
3. So then the limit goes from negative c over 2 to c over 2. That's your final integration now. Okay. Now if you do that, okay, let me show you my nice calculation on the slide. This is not so much nice. So if you do that, then you know I exactly got this one here so far. I got this one exactly here. This is what I got. Then simply have to plug in the value of c over 2 and negative c over 2 right here. Then you end up getting this. Okay. So far so good, right?
I think so.
Okay, now we did just only one. So we're done with this IXX. Now we have to do all those 3, all those 9. Actually 5 now because they are exactly the same, right? So we have to all do all those 5. So similarly now, but even though we have to do all 5 in principle, we can conclude that if IXX is B square plus C square times M over 12, then what do you think your IYY be? Help me here. So XX meaning, if you have XX, then you have B square plus C square. So if you have YY, so remember this one, B is Y dimension and this is Z dimension, Y and Z, right? B is Y dimension in the Y direction and C the dimension in the Z direction.
Then you'll have A squared plus C squared.
Exactly. So if you want to do G, then you have to have A square plus B square. So you don't have, you don't have to do the derivation, you know, it just follows. Cool. So just use the symmetry, okay? Now similarly, let's do one more thing here. Let's do IXY here. Then similarly, other also follows. So if you do IXY, right, IXY, then what is the formula? Negative triple integral XY rho. Similar, if you have XY here, then you have also XY here. Okay. So IXY equals negative triple integral XY, then rho, you know, the volume element here. So these are all common. Rho volume element, rho times volume element, rho times volume element is common. Only this guy varies as you go down. XY becomes XZ because this is XZ. And similarly, this guy becomes YZ because this is YZ. So let's do one of them. Let's do this one. Then the other 2 follows. Okay. So IXY, right? Let's do IXY. Then negative C over 2. This is the limit. Then XY rho dx dy dz. Okay. Then let's do the integration with respect to dx here. Integration of this guy with respect to dx. So you actually, sorry, y you can pull it out because y is constant, right? You can pull this y here. Y is constant with respect to x. So you simply pull this y here. Does it make sense? Then what is the integration of x? X square over 2. That's what it is. Okay. Then a over 2, negative over 2. What is the integration of? What is this guy here? What is this guy? So if you do that, what do you get here? Help me. If you plug in the value of the limits, then you get x square over 2, which is a square over 4 minus negative a square over, sorry, negative a whole square, it will get, you will get a square again. So a square over 4 minus a square over 4 divided by 2. So which is 0, right? So since this guy is 0, then everything, the entire term is 0. Now you can guess similarly, these all those guys are 0, 0. These all three are 0. This is what we wrote here too. See, if the mass distribution of the body is symmetric with respect to body attached frame, then the cross product of inertia is identically 0. That's what we claimed here. And that's what we found here, because so body axis, so body attached frame, this is the body attached frame. So with respect to, this is symmetric with respect to x, meaning this coordinate frame divides the x in half, y in half, and g in half. This is because this is right in the center. That's why all those ix cross terms will be 0. So you don't have to even do this. You don't have to even do this calculation, because you know this is symmetric, right? That's why you can simply say, because of this argument, you can use this argument and say that is 0. You don't have to even do the calculation. Does it make sense so far?
So x, y, x, z, y, z, those are all equal to 0?
Yeah, because these are all called cross term, right? Cross meaning they have the x, y, y, z, and zx term, right? They are cross. That's why you call it cross product of inertia. And these all will be 0 as long as, okay, the body is symmetric with respect to body attached frame. As long as it is symmetric, okay? So this is what you need to make sure. If the body is symmetric with respect to body attached frame, then all those things are 0.
I guess I'm not understanding what the symmetry means.
Oh, okay. Symmetry means, so does this because this is at the very center, right?
Okay.
So does this point divides the x direction in half?
Say again, sorry.
So does this point divide your x direction in half?
Does it divide our x direction in half?
So because this is right in the middle, right? This is right in the middle. So this is the middle of x direction, middle of y direction, middle of the g direction also.
Okay, right.
Does it make sense?
Yeah.
So that's what I meant by symmetry. So divide in half in the x direction, divide in half in the y direction, divide in half in the g direction of the object.
Okay.
That's called symmetry.
Okay.
Make sense?
I believe so.
Okay.
Thank you. Thank you.
All right. So let's move on to the next one. So then you can just conclude, you can make this matrix now. So you know your so these are all zeros. These are zeros and this is zeros. So then you have just the component here. So you found I there, I matrix, okay? That's how you figure out I. All right, let's do one problem with the coordinate polars, cylindrical polar coordinates. Have you guys done this before? Cylindrical polar?
No.
No, okay, that's fine. That's fine. So I'm just wondering. So what is, so far we did the Cartesian coordinate, X, Y, Z, right? So our coordinate system was just how long, how far do you go towards the X, then Y, then Z, right? That's how you locate the point. Now, there are other kinds of coordinate system as well, okay? So one of them is cylindrical coordinate system. So in that case, instead of denoting the point by X, Y, Z, we denote that by R, phi, and G, okay? So what I meant is, suppose you have to figure out the location of this point, right? Then what you do is, so how far you have to go. Okay, so let's do the phi first, okay? So this point is here, and what is the angle from here to here to here? This is phi. Then how far you have to come from the center, the origin? This is R. Then how high you have to go? G. R, phi, and G. That's the cylindrical polar coordinate system. So instead of using X, Y, Z, you could also use R, phi, and G. Does it make sense?
I think so.
Okay. So this kind of coordinate system is mainly useful if the object in question is cylindrical. Okay, now like if you have this kind of system, right, then XYZ is good. XYZ coordinate system is good. Okay, XYZ. That's what we did here, right? So dx, dy, dz, that's what I meant. But the system, if it is cylindrical like this, right, then you have to do the, not have to, but this is much easier. Okay, so cylindrical polar coordinate system is frame is much easier in this case. Okay, if you have the system like this. So here, what is your, suppose you if you want to consider this volume element. So in the previous case, what is the volume element? Dx, dy, dz, right? Small chunk, right? Having dx, dy, dz, right? Okay, if you consider very small chunk here of the same rectangular shape, not as shown, as I drew here. So make the rectangular one right here, rectangular small chunk right here, and call the direction to be the elements to be dx, dy, and dz, right? Small. What I'm saying is the smallest version, small version of this picture. Okay, small version of this picture right in the middle. If you make that, the dimension of that guy will be dx, dy, dz, right? Similarly here, let's figure out the volume element of this cylindrical coordinate. So you see the red thing here, right? This is the volume element of the cylindrical coordinate. So how do you define this volume element? So we have R, phi, and G, right? Okay, suppose from here to here is R. Then we need to worry about this only, right? Then this is dr. Assuming this is R, from here to here is R, then this is small volume element, the dimension, this dimension is dr. Okay, so we are done with dr here. Dr is done. Then let's talk about phi. So d phi, right? So you have to go from here to here. If you want to go from here to here, how much do I have to rotate? You have to rotate by a small angle, which is d phi. That's my d phi. Yeah, go ahead. Then I have to do the G here. What is your G? Which is dz. this is EG. Okay, so as in the previous XYZ, this is DG is vertical height, right? So this is very simple. Okay, then how do you find the volume of this guy now? Again, we can consider this. This is the small, infinitesimally small, right? Very, very small, right? This is dV. This red thing is dV, right? This is dV. So in calculus, what is dV? Tiny, tiny, tiny element of the material, right? Or object. That's the dV. In other words, even though you see this red portion of the cylinder looks like very big here, in principle, that's very, very small portion of the cylinder. Then if it is very small, then the volume of this small element is x times y times z, right? In our system. So what is your, so meaning, so your, I don't know, length, I don't say, okay, no, okay, I'll take it back. So I don't say x, y, z, but I will say length, width, and height. Let me put that way, okay? So if I call this the length, dr is the length, right? Then what is the width of this guy? This is the width. Then I have to do the height, length, width, and height. That's the volume of this guy. So length is dr. Length is dr. There. Length is dr. Okay. So then what is the width? Help me. The width is this one, right? From here to here is width. How much is width? If this is the angle is d phi, right? If the angle is d phi, okay, and the radius is r, then what is this? What is the width here? Help me here. What is the length of this one here, from here to here? R times angle.
Oh, okay. I thought I had something.
Arc length, right? Arc length. Remember in the circle, what is the arc length? Radius times angle. That's the arc length.
Okay.
So r times d phi. That's my width. R times d phi is the width. Both of them together. R times d phi. This and this constitutes the width. So we have the length, dr. We have the width, r d phi. Then what is your height? dg. That's your height, dg. That's how you figure out your volume in the case of cylindrical polar coordinates. Small volume, right? Volume element, rather. Guys, question here, please. If you have cylindrical robot, you might have to, do this kind of calculation.
Okay.
So I want to make sure you guys understand dV. So that's what I want for now. dV equals this guy.
So dV is our volume.
Small volume element. Now we are going to do the integration, right? Remember in the integration, we take the small element, then do the entire integration, put the limit.
Okay. Cool.
Okay. Now let's use this formula again. We have the formula here, right? So we have to use those formula here. Those formula and find this I again for that for this picture. I have different problem here, by the way. This is same solid cylinder, but yeah, I have nice picture here. All right. Then let's figure out IGZ first. Then we'll figure out others also. Okay. Last time we did XIX. Let me start here with the IGZ. What is your IGZ in this case? Again, the formula is the same thing here, right? What is IGZ formula? IGZ is x square y square rho dx dy dz, right? So instead of saying dx dy dz, we have, instead of this, we had to put this value here. We had to put this guy here. Instead of dx dy dz, we had to plug in this here, this thing. That's the only difference, okay? So that's what I did here. R dr d theta dz, that's my dx dy dz. Okay, then rho is there. Then, so what do you have there? You have x square plus y square, right? X square plus y square. Let me consider this is my x direction, this is my y direction, right? Then what does x square plus y square give me? Suppose this is xy, right? Suppose this is xy. So then what is the x square plus y square? Help me here, please. I'm lost.
What was the question again? I'm sorry.
So this is, suppose this is xy coordinate, right? So this is xy. This point is on the xy plane, right? So I can say this is x square plus y, sorry, xy. This point is, oops, this point is xy. So what I'm asking is, what is the relationship between xy and r?
R is would be the cosine of x.
This is
No,
what
I
I'm
don't think that's the
asking.
right thing I want to say.
Yeah, I think, okay, I have to ask. So this is y, right? This is y. From here
Right.
to here is y. And from here to here is
X.
x, okay? So if you square x and x square plus y square, you get r square, Pythagorean theorem.
Always okay.
X
It's
square plus y square equals r square, right?
okay, right.
So that's what I meant. Now, so we had x square plus y square here. See that? This is x square minus y square in the formula. For IgG, we are doing IgG. So this x square plus y square happens to be r square in this coordinate system. That's what I did here. See, I replace x square plus y square by r square. Yeah, this is the only step we have to understand. Rather, other things, following steps are, the steps that follows are very simple. As long as you understand this step, we're almost done.
Just a quick question about something I'm just a little confused on is what is with the density times XYZ? Because when we were doing IXX, that we didn't throw that in there.
Density times XYZ. Yeah,
where we got the R squared density XYZ in parentheses.
Yeah, so what I meant is, this is the general formula, right? This is general formula. What I meant is,
right,
a material may not have uniform density, right? Not all the material. Suppose you take an object here, right? Suppose this is an object. So these materials here, material at this end might be different from the material here and here and here. In that case, density is function of XYZ. Okay, but in our particular problem here, right here, this density is not the function of XYZ. This is constant.
Oh, so in our IXX example, density was technically given to us.
Yes. So that is also, yeah, that is also constant. So here also this is constant. Even though I wrote XYZ here, in principle, the density can depend on XYZ, right? Okay, depending on the material. Suppose this guy is made of different materials. So suppose, so up to here is silver, up to here is gold. Then you have the lead, right?
Okay.
Then if you go from here to here, the density varies, right? So I'm not giving you this kind of example, this kind of material. I'm just giving you, a material which has uniform density, an object which has uniform density. So made of same material, I would say in this case, made of let's say copper.
Okay.
So in that case, my rho xyz is constant. So even though I write as a function of xyz, in principle I write that way, but in my particular example, this is constant.
Okay, thank you.
All right. So now does it make sense so far? So this is dv in the cylindrical coordinate, and rho, obviously this will be constant, right? I'll consider this as constant in this example too. Then x square plus y square is r square. Now let's choose the what do we have to choose now? The limit of integration. Okay, so we have three variable here, dr. For dr, what is the limit of integration? So you go from here to here, right? Meaning from 0 to r1. Okay, that's my limit of integration here, 0 to r1. dr is done. For d theta, what is the limit of integration? Theta. It goes from 0 to 2 pi, right? That's my limit of integration, 0 to 2 pi. Then we have to do the dg, right? What is the limit of integration for dg? So if the height is h, and we're assuming this is at the center, right? Then my dz limit of integration is negative h/2 to h/2, right? Does it make sense? Guys, question please.
If just going back just a little bit. Oh no, same page. My bad. When we were talking about our x squared, y squared, I understand how we got the r squared, but why is it we have the r dr d theta dz?
Because we have to have the volume element, right? See the formula here. So here, what is the formula? This is so much messy. Let me clear this up. So for the GZ, right? We are doing GZ, right? So for the GZ, so this is actually dV, okay? In Cartesian coordinate system, what is your dV? In Cartesian, you have dx, dy, dz, right?
Oh, okay. I think I'm seeing now. What I thought was we were replacing that with dv. Just we had to find our r. So r is just always gonna. Okay, I think I get it.
Okay, so this is r square, right? This is r square. Then rho is rho. Then dv is replaced by this guy here. The dv is replaced by this guy.
Okay.
Make sense?
I believe so.
Okay. All right. Thank you guys. So good. So now the rest is just the integration. I don't think I have to go through this, right? So I think you guys, the way we did in the previous problem. So just do the integration here. First do this integration here. Finish this one. So r square, you don't have to worry about rho. So r square and r, right? You have r cubed. Then r cubed dr. What is the integration of r cubed dr? So r to the 4 by 4, that's my integration. Okay. Then similarly, you can follow this along, and I think it should be good. If you do that finally, and I plug this in here. One thing I replace here is this guy here. I factor this out because this is the mass of the cylinder, right? rho times, so pi r square h is volume, right? Volume of the cylinder. This is the volume and this is the rho. Rho and volume multiplied, if you know, the product of rho and volume is the mass, right? So that's what I did. So the m 1/2 r1 square. So that's what you get. So, yep, so that's how you do it. So similarly, yeah, similarly, you can do the other calculation too, okay? Use the same formula again, this formula, use the same trick. So you need your dV, right? dV is all, you know, is same all the time, meaning your dV is this all the time. Whatever integration you do, your dV is always this. You just replace all of the dV by that. Okay, then you do the integration. That's how you figure out. Okay, so unless you guys have any question, I think I should close my shop.
I don't think so.
Okay.
I think I'm good.
All right. Thank you so much, guys. Stay safe.
Same to you. Thank you very much. Have a
So,
nice day, Professor.
so yeah, so I'll as I said earlier, I'll post the quiz today on the Moodle.
Cool.
All right, guys. Bye now.
Take care, everybody.
Bye-bye.